Welcome back, everybody. We're going to continue looking at the Csmc paper from the year 2014 in this video. If you don't have a copy, of course, click the link in the description and you'll find yourself at the Csmc website, and you'll be able to download a copy of this and several other papers. So we're about halfway through Part B, which is the written portion of the contest. We're on to question number 2 now. So how about we take a look at it together? All right. So 2A. In the diagram, looks like we have 2 parts, 2A. That's odd. I guess they're connected in some way. In the diagram, semicircles are drawn on the sides of a right-angled triangle, X, Y, and Z, as shown. Okay, X, Y, Z, and we've labeled the sides already X, Y, and Z. If the area of the semicircle with diameter YZ is 50 pi, and the area of the semicircle with diameter XZ is 288 pi, determine the area of the semicircle with diameter XY. Okay. Well, it's a right angle triangle, so if we can figure out X and Y, which we should be able to knowing the area of the semicircles, then we could figure out what Z is, and from there figure out the area of the semicircle. Okay. So we'll draw a copy of our picture, as we so often do. We can draw a better hypotenuse than that, can't we? So 1 semicircle, 2 semicircles. Here we have Y, Z. Y, X, Z, and Y. Alright, they're not exact semicircles, but that's okay. We know that this is 288 pi, and we know this is 50 pi. Okay. So YZ, XZ, XY, YZ. Are diameters of semicircles. And so a semicircle with diameter D has area, well, it's 1/2 of the circle of diameter D, and circle area is pi r squared. So pi r squared, well, r is half of the diameter. So pi d divided by 8. Oh, pi d squared, sorry. Pi d squared. That could have really seriously damaged us. Okay. So 288 pi is pi times YZ squared over 8. I don't know why I keep saying YZ. It's XZ. So XZ squared is going to be 8 times 288 times pi divided by pi. So those will cancel out. And we'll be left with 8 times 288. 2304. So 2304, square root of that, I believe it's 48, but let's just double check on our calculator. Fantastic. Alright. Likewise, we have 50 pi is going to be pi over 8 of YZ squared. So YZ squared is going to be 50 times 8 times pi divided by pi. So 50 times 8, that's 400. So YZ is the square root of 400, and that one is definitely 20. Okay. So XZY is right angled. So XY squared is equal to XZ squared plus YZ squared. Well, hey, we didn't even need YZ and XZ. We already had their squares. So that's 2304 plus 400, 2704. Now I'd square root this and find xy, I really would, but it turns out we're not going to need that. Incidentally, xy would be 52, but look at our formula, we need d squared. Well, we already have d squared. So we have area of pi by 8 of xy squared. Well, that's pi 2,704 divided by 8. Well, 2,704 divided by 8, that's 338. 338 pi. Okay, and we've explained how we got it. We derived a formula for the semicircle area. Fantastic. Now for A, part 2, which should have some connection. In the diagram, squares with side lengths P, Q, and R are constructed on the sides of a right-angled PQR. So we have triangle PQR, and we have side lengths PQR, and then we construct squares of those side lengths. Diagonals QT, RU, and PS have lengths A, B, and C respectively. Prove that the triangle formed with side lengths A, B, and C is a right-angled triangle. Okay. Well, let's draw ourselves a copy of the diagram. We have R, we have P, we have Q, and then I cannot remember the names of the. I know it's STU. I just don't know where they were. So QT, RU, and PS. So STU, counterclockwise. Okay. Well, notice we have a bunch of right-angled triangles here. And that means that A squared, which is TQ, is going to be, let's write this a better way. TQ squared is going to be RQ squared plus RT squared. So A squared is equal to P squared plus RT squared. But since it's a square, RT equals RQ, which was P. So A squared is equal to P squared plus P squared, or 2P squared. In the same way, we can get B squared and C squared are 2Q squared and 2R squared, respectively. Now we already know that P squared plus Q squared is equal to R squared because we were told that PQR is a right angle triangle. So if we multiply by both sides by 2, we don't change the fact that we have an equality here. And we can work our way down and show, using our new information for A squared, B squared, and C squared in terms of P, Q, and R, we can show that A squared plus B squared is equal to C squared. By Pythagoras, we get a right angle triangle. Because the relationship between the side lengths A squared plus B squared equals C squared is only satisfied if A, B, and C were on a right angle triangle, specifically with hypotenuse of length C. Okay, that can only happen, and whenever that happens, you have a right angle triangle. So there, we were able to show exactly what we were asked for, that A, B, and C form a right angle triangle. Okay, so that was A part 2. I'm not exactly sure how related it was to part 1, but then again, there are probably lots of ways to do these questions, and there might be a really nice, elegant way of doing 1, or even 2, and they have a similar style of solution. I'm not entirely sure. I will remark that we had an area of, what was it? 338, right? 338 is 50 plus 288, so there's probably a really nice Pythagoras right angle triangle way of doing this. Not entirely sure, but there's likely a way of doing it. We'll do that we'll leave that for another day. So, B. In the diagram, triangle X, Y, and Z is right angled at Z, and AZ is the altitude from Z to XY. Okay. Also, segments AD and AB are altitudes of AXZ and AYZ, respectively. And segments DE and BC, well, those are more altitudes for ADX and ABY. Prove that AE is equal to AC. Okay, so if we have a right angle triangle, we drop the perpendicular opposite the right angle, and drop 2 more perpendiculars, and then perpendiculars after that, we should always have same length there. That's actually kind of nifty. Let's see what we've got. So it'd be a very good idea to draw a very big copy of our picture, because I have a feeling we're probably going to do a little bit of diagram chasing. There might be some trig, there might be some angles. I have a bit less of a steep line. Alright, so we have a right angle here, Z, X, Y. We have A. Right angles here. Right angles here. And obviously it's not going to look like it in my diagram, but we want these 2 lengths. This is A, this is C, and be DF here. So we want AE equals AC. Okay. How are we going to do that? Do I have the diagram copied correctly? Let's just check that. Yep, absolutely. Okay. So, well, the first thing that strikes me is not anything down here, but we seem to have a rectangle here. So, since angle ADZ, angle ABZ, and angle XZY, then angle DAB, so ABZD is a rectangle. Okay, does that help us? I don't know, but it's definitely there. So I'm going to mark this thing up in, we'll go with the pinky red. So what did we just learn? We learned we have a right angle here. Okay. Now, I wonder, so we'll use blue for my wonders. That means that AB is equal to DZ. Okay? And so if I were to not drop this altitude, but instead drop this altitude, I would have DZ is equal to AB. I would have another rectangle right here. So this length would be equal to EA. I wonder if the angles here are equal enough to get ABC. Well, actually, knowing that that has to be the answer, this has to be AE, then this definitely, since it's a right angle triangle, will have to get the angles there be the same. But is that something we can prove without first proving that AE is equal to AC? So let's call this guy F. So we're going to let F be the intersection of the altitude of DAZ and it's the altitude coming from D. Okay. So notice that angle DFA, angle FAE, and angle AED are 90 degrees. So once again, we can conclude, just as we sort of did before, DFAE is a rectangle. Okay. So we've got rectangles, and we know, although we haven't stated yet, AB is DZ, and EA is DF. Okay. I guess we're going to have to do a little bit of angle chasing. So we'll use green, and we'll say that this is theta. So we have theta, we'll have 90 minus theta. This one in here is also 90 minus theta. Fantastic. That's a 90 degrees there, so that's theta. So that'll be 90 minus theta. And that means that will be theta. And so we're going to have similar triangles, or congruent triangles, so that'll work. Okay. We get back to black. So angle ZAY. No, let's say let theta equal angle BAC. Angle ZAC is 90 degrees. So angle ZAB equals angle ZAC. Zac minus back. So we get 90 minus theta. Okay. Angle ABZ, well, that's also 90 degrees because AB was an altitude. Angle ABZ plus angle ZAB plus angle BZA. Interior angles of a triangle, it's 180 degrees. So angle BZA is 180 minus 90 minus 90 minus theta, which is equal to theta. Now angle BZD is 90 degrees. And that means that angle AZD is angle BZD. I'm just copying, if I had the diagram handy, this would be a lot easier. I'm trying to remember the diagram off the top of my head. Minus angle BZA, which we just worked out. So this is 90 degrees minus theta. Okay. And I think this will be the last one. Angle DFZ is 90 degrees. Angle DFZ plus angle AZD, which is the same as FZD if you take a look at the diagram, plus angle ZDF is 180 degrees. So angle ZDF is 180 minus 90 minus 90 minus theta. And that's going to be theta. So triangles ZDF is similar to triangle BAC. Fantastic. But since we have a rectangle, ZBAD, that means that BA is equal to so rather than just being similar, we actually have that they're congruent triangles. So triangle ZDF is congruent to BAC. So what does that tell us? That tells us DF is equal to AC. But DFAE is a rectangle. So DF is equal to AE. And so we finally conclude AC is equal to AE. Okay, so let's go back and see how our diagram helped us achieve this. So first thing we did, we noticed that there was a right angle here, and that gives us a rectangle. And then we dropped the altitude DF, and we created ourselves a second rectangle. And we used a little bit of angle chasing, and I admit that was a bit of long writing, but it had to be done. With theta, 90 minus theta, 90 minus theta, theta using this right angle triangle here, ZAB, then 90 minus theta, and then this 90 degree, because DF was an altitude, means we have a theta here, and that means that these guys are similar. But because we have a rectangle, these lengths are actually the same, DZ and AB. And if they're similar and they share a side length, then they're going to be congruent. And that told us that well, DZ is AB, ZF is the same length as BC, and importantly, DF is the same length as AC. And DF is part of a rectangle, so DF was the same as AE, but DF was AC, so AC equals AE. So certainly a good idea to drop that altitude at F, and then it was a bit of diagram chasing with the angle, although not that much. And yeah, we got our final answer. Well, not an answer, but we proved, and we proved rather nicely, I would say. It's actually quite a short geometry proof considering some of the other ones I've had to write. But yeah, we got it. AE equals AC, and that's kind of a cool little fact about right angle triangles here. If you drop the altitude and then drop 2 more altitudes and then 2 more altitudes after that, they're going to be the same distance away from the original altitude. So that's kind of nifty. And that concludes question number 2 on the 2014 paper. So we just have one more question to go, question number 3. But as usual, we'll save that for another video. So I'll see you guys in the next video as we finish off the 2014 paper. So thanks for watching.